Testing. Testing, testing, testing. Testing. Testing, testing. Testing, 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 testing. Testing, testing. Is this not live? What is going on? Good morning, Ed. How's it going? Is it morning, Ed? How's it going? All right. Happy Monday, everyone. Thanks for tuning in to the Hoopo stream. Today we're going to be looking at a paper called From Sparse to Soft Mixtures of Experts. So, two different types of mixtures of experts here, basically sparse and then soft. And sparse is a reference to earlier work. So this team is out of Google DeepMind. This paper released on the 2nd of August 2023. But important here are these two first authors here. And those two first authors are also the first authors of this paper here, which is from 2022. So over a year ago, they introduced this paper called Sparse Mixture of Experts. So basically what this paper is, it's kind of the extension to that, and they're going to be talking about soft mixture of experts. And there's an even earlier version of all of this work, which is called Pathways. This is October 2021. So basically the rough genealogy of this thread of research is coming from this 2021 paper, then this 2022 paper, and then finally this paper here. So I was intrigued by this paper because of this blog post that I read, where basically this guy here, Simple Thoughts, this is the blog of a engineer who works at 11 Labs. So if you guys have heard of 11 Labs, 11 Labs is the company that does all the speech cloning. I used it in some of the videos before. I've used it in some of my projects. It's one of the better speech cloning services out there. But anyways, this guy, 152334H, which by the way, great name. He wrote this blog article on how basically GPT-4 and 3.5 are non-deterministic, and what he means by that is that you give it the same input, produces different outputs, and that kind of gives you a little insight about what might be happening underneath. And he kind of dug deep and eventually figured out that maybe this has to do with the way that they're implementing the mixture of experts. It's kind of already been not necessarily fully confirmed, but pretty much confirmed that they're using a mixture of experts approach for GPT-4 and GPT 3.5, and he kind of goes one step further and says that not only is it a mixture of experts, but it's specifically a sparse mixture of experts, which is a technique that Google DeepMind has pioneered, specifically this research group within DeepMind. How's it going, Ed? How's it going, Luke? So that's a little bit of background and context for this paper. All right, so then let's just get right into it here. Sparse mixture of expert architectures, MoEs, scale model capacity without large increases in training or inference costs. So model capacity is another way of saying the size of a model, right? Big models have a lot of capacity, but here they're saying that you're going to do that without increasing the training or inference cost, right? So the problem with these bigger models is the bigger you make the model, the more neurons there are, the more parameters there are, the more times you have to basically calculate things inside your GPU or your CPU, and therefore your training takes longer and your inference takes longer. And it's not just the amount of time, it's not just the time complexity, it's also the memory complexity. Okay. So despite their success, mixture of experts suffer from a number of issues: training instability, token dropping, inability to scale the number of experts, or ineffective fine-tuning. Okay, so I don't really fully understand all the different reasons why MOEs have these exact negatives, but here's a bunch of negatives associated with MOEs. In this work, we propose Soft MoE, a fully differentiable sparse transformer. So fully differentiable just means that you can take the derivative of everything in this Soft MoE, which means you can take the gradient, which means you can backprop and train it. A transformer is just a type of model architecture that has this attention mechanism. A lot of different AIs now use this. Sparse is basically just the opposite of dense. So something that is sparse has a lot of zeros and very few non-zero values, and something that is dense has a lot of values and not a lot of zeros. There's more specific definitions of that. While maintaining the benefits of MOEs, Soft MoE performs an implicit soft assignment by passing different weighted combination of all input tokens to each experts. Okay, so this is going to be basically I think the key contribution of this paper here is that you're going to be weighting combinations of input tokens to each expert. And I found this here. So this is the original, or the blog post for Sparse Mixture of Experts, but I think it has a good figure here that explains kind of what's going on, right? And to explain what's going on here, let's, transformers, attention is all you need. Let's look at the original transformer picture here, which we've shown plenty of times. But here in a transformer block, right, so one of these gray circles here, or what is this, rounded rectangle is called a block, and there's n of these. But you notice how there's an attention head, or an attention computation here. There's this add a norm, which is a layer norm, right? And if we go here, you can see the equivalent. So here's the attention. Let me actually pull it separately here so you can see both of them side by side. Open image in new tab. Why is this not working? What is this? Open image in new tab. All right, there we go. Okay, so your layer norm, you have a layer norm beforehand. Usually there's layer norms before now as well, but here they have a layer norm before and after. You have your residual connection here going around the attention head. You have your residual connection here going around the attention head. And then you have another layer norm, which they have here. And then you have the residual connection going around this feed forward block here. But the interesting thing to look at here is the difference between this feed forward block and this feed forward block here. So here, this feed forward block, this blue block, just represents basically this. So I'm pulling up 400 different things at once, but I think it's the best way to explain visually. That's the way I love to do it. This is a visualization that I love to show sometimes, and this is the visualization of a convnet used for classification. So at the very bottom, I have the input, and let's say if I put and I draw a 2. So this is the input, and then this is showing you all the different layers of this convolutional neural net and what the activation is for each. And you can see that at the very end, so at the very end of this classification model, we have the outputs, which is basically one neuron for every single possible digit, and then you can see how if I draw a 3, you mostly get the 3. So this is the classification model is working correctly. But the reason I'm showing you this is to show you these last 2 layers. So these last 2 layers here are a fully connected neural net, right? And what is the fully connected? Just basically means that for each one of these little neurons, if I hover over it, you can see how there's a line connecting it to all the neurons previously, right? And this is usually called the model head, right? And this is called the model body down here, sometimes also called the encoder. There's a million different backbone, is another name for it. But specifically, let's look at this model head here, right? And this is the feed forward. So this blue brick here represents something that kind of looks like this. It represents a little fully connected feed forward layers, right? And if we go back to the mixture of experts, we've replaced this single feed forward with a mixture of sparse experts, right? So here you go. We replace some dense feed forward layers with a sparse mixture of independent FFNs, which we call experts. So rather than having just one layer here, we're basically going to have a bunch of different independent layers, and each one of those is going to be called an expert. FFN1, FFN2, all the way to E, right? You have E of these. And then you're going to have a router, or some extra little piece that determines where to send the different inputs, right? And let's take a step back and think about, why would we want to have maybe a bunch of these rather than just a single one, right? Like, why would we want many of these rather than a single one? And I think one thing to realize is that these fully connected layers like this there's a lot of wasted compute in them, right? So even just here, right? So we put the number 3 down, and then it goes all the way through our neural net, and we get the number 3 up here, so we're correctly classifying. But look at the values for this fully connected neural net. Like, if I go here and I click on one of these, what is the value for this? It's 0.23, 0.18, 0.36, 0.04, 0.045. So if you actually realize it, a huge amount of the neurons here are not even doing anything, right? So really, the neurons that are actually making this classify correctly as a 3 are these ones here that are brightly colored, right? So you notice how most of our prediction is coming from a very small handful of the neurons, and most of the other neurons are basically just numbers that are very close to 0. So the intuition that I want you to get here is that for these type of feed-forward neural nets, you're spending all this time on your GPU multiplying a bunch of very small numbers with a bunch of other very small numbers to then multiply those by another small number and another small number, and ultimately, at the very end, it wouldn't have really impacted your computation, right? So if you could have only just gotten rid of all the compute that you would have wasted just calculating these small numbers multiplied by other small numbers, you would have probably gotten pretty much the same answer. And that intuition is kind of the key intuition behind this pathways, right? Which is, let's basically create a sparse version of our model, and then we have this extra check of not only is it sparse, but then we have a mixture of these sparse versions. And it turns out that if we basically use that mixture of these experts, we're going to get a better answer at a fraction of the computational cost. Okay. How's it going, Joseph? So that's kind of the key intuition here about why we're doing this mixture of experts, is basically we get better answers for a lower computational cost. And the reason that happens is because most neural nets are mostly 0, where a lot of the neural net, a lot of the matrix multiplies, a lot of those little values are zeros, and there's really only a few pathways through the neural net that matter. Okay, so there you go. That's largely why we're doing this. Now let's go back to the abstract here, and let's go. Okay. So as in other mixture of expert works, experts in Soft MoE only process a subset of the combined tokens, enabled larger model capacity at lower inference cost, which is kind of this intuition that we were just building there. In the context of visual recognition, Soft MoE greatly outperforms standard transformers and popular MoE variants, tokens choice and experts choice. So tokens choice, expert choice, and weighted combinations, these are all just referring to different ways of doing this router, right? At the end of the day, all these MoE techniques are basically the same. It's just you have a mixture of experts, and now the nuance comes in, and how are you routing the output of these attention matrices into these different FFNs here. So you have different techniques here. You have, okay, tokens choice probably is the token itself has something that determines where it is. Experts choice means you maybe have an expert router like this, right? So there's different ways of doing that. And this Soft MoE is basically just the latest way of doing that, which is some kind of weighted combination. Okay. Soft MoE base 16. So this is a vision transformer is what they're going to be using to demonstrate this technique. So in a vision transformer, you're splitting up the input into I love this GIF that they have here as well. So in a vision transformer, you start with an image and then you break it up into the little patches, and each of those patches are called tokens, right? And that's kind of analogous to the way that language models work, where the sentence is broken up into these little patches called tokens. Here, in this particular version, which is Sparse MoE, you can see how basically there's this router and it scores each of the tokens, and then depending on the score of the tokens, they get routed to different experts. But the important thing here that I was showing you is that an image is broken up into these patches, which are called tokens. And this is the VIT that they're using. Okay, so they got 10.5 lower inference cost, which leads to 5.7 lower wall clock time. Testing, how's it going, Christopher? While matching its performance after similar training. Soft MoE also scales well with 128 experts in 16 MoE layers, has over 40 times more parameters than VIT Huge, while inference time grows by only 2%, and it performs substantially better. Okay, so there you go. It's basically, the whole reason for doing this is you get better performance, a bigger effective model capacity for a smaller inference time, smaller compute, smaller memory. Roger, what's your vector, Victor? What is that? I'm not cool enough to understand that reference. All right. Larger transformers improve performance at increased computational cost. Recent studies suggest that model size and training data must be scaled together to optimally use any given training compute budget. A promising alternative that allows to scale models in size without paying their full computational cost is a sparse mixture of experts, right? So without paying the full cost. Recently, a number of successful approaches have proposed ways to sparsely activate token paths, right? Here's that word path, token paths, kind of coming from this pathways, right? Where you have different paths that the tokens will take, right? Kind of analogous to what's going on here, where this pathway that the information took to get to this final neuron here that represents the concept of 3, it went through here, it went through here, it went through here, it went through here, and all the way it goes back down to your input here, which was the raw input 3. And actually, the interesting thing I like to do here is I actually like to erase. So let's say something like that, right? So if the input was something like this, the convnet is actually confused. It has some activation on 3 and some activation on 1. Okay, at the core of sparse MoE models lies a discrete optimization problem, deciding which modules should be applied to each input token. These modules are commonly referred to as experts, okay, and are usually MLPs. Okay, so discrete optimization problem, it basically comes down to what they're saying here. Which expert are you sending the tokens through, right? Which of these FFNs, feed-forward networks, multi-layer perceptrons, fully connected neural networks, which one of them are you choosing to send the specific tokens? Which pathway is a token traveling through? Which expert is that token going through in order to get to the very end? It's a line from an old movie. You're dating yourself. Slap me a bit of the porterhouse. I don't get these references. Many techniques have been devised to find good token-to-expert matches. Linear programs, reinforcement learning, deterministic fixed rules, optimal transport, greedy top K experts, greedy top K tokens. So these are just different ways of routing. In many of these cases, heuristic auxiliary losses. So a loss is what you're using whenever you're optimizing, whenever you're training a neural net. An auxiliary loss is a loss that is auxiliary to your main loss. So you'll have your actual loss that you're wanting to optimize, but then you have extra losses, and some of those losses might help regularize your solution, right? So it might I'm trying to think of an example of some kind of auxiliary loss, but maybe an auxiliary loss would be like it has to match the depth or something like that. But a heuristic auxiliary loss is a loss that you're hand designing and that is auxiliary to your main loss. are required to balance utilization of experts and minimize unassigned tokens. Minimize unassigned tokens, the tokens that are not routed through any of the experts. These challenges can be exacerbated in out-of-distribution scenarios, small inference batch sizes, novel inputs, or in transfer learning. So scenarios that are outside of the distribution of your training data, such as transfer learning, whenever you're trying to take your model which you've optimized or performed training for a specific data set, and then you now want to apply it to a new data set that is out of distribution of the original training data set. Novel inputs are also part of that. And small inference batch sizes, this is basically when you're training, you have all your data ready to go, so you can pick the biggest possible batch size. But when you're performing inference, which is when you're actually using this model in the real world for some purpose, you don't have a full batch of data, right? Oftentimes you might only have a couple examples, and most of us, when we're doing inference at home, we're using a batch size of 1, right? So you're only having one image that's going in and that you want your output to. So inference batch sizes generally smaller and potentially different sizes compared to the batch sizes that you use in training. Okay, we introduce a new approach, Soft MoE, that overcomes many of these challenges. Rather than employing a sparse and discrete router that tries to find good hard assignment between tokens and experts, Soft MoE instead performs a soft assignment by mixing tokens. So sparse and discrete router is exactly what they did in their previous work, which is this one right here, right, where you have a router that takes every single token in your input and then sparsely routes it. So the sparse there refers to the fact that some of them don't actually go through. So only the experts have a limited amount of inputs, and you can see how only some of the tokens go through. So what they're going to be doing is they're going to be doing soft assignment by mixing tokens, which is kind of a crazy idea. And here they actually show you the picture. They use the same picture of the duck, which I love. I love when research like this that spans multiple years uses the same examples in their figures, because it allows you to go to previous papers and see the exact analogous example. So here we see they've decided to keep using this picture of the duck. They're breaking it up into these patches. The patches, you could think of them as tokens. The tokens are going in and they're being basically here routed into specific experts, which is what's going on here. This is in their original work. You see how the tokens are routed to different experts. And that's called Sparse MoE, right? Soft MoE, which is what this paper is about, they're going to average the tokens. So if you actually see it, this token right here is not actually any of the tokens in this image. It's an average, it's a weighted average of multiple tokens. So you can see how it's part of this image here, the back of the duck's head. It's part of this image here, the side of the duck, and you see how there's a little weight for each of them. So it's 0.09 of this, 0.4 of this, 0.03 of this, 0.01 of that, 0.3 of that. So you can see how it's like a weird average token of multiple tokens. And then those are given to each of the experts. So no longer are you sparse, right? No longer are you only giving some of the tokens to the experts, right? So this high capacity case is not what we're interested in. We're interested in this limited capacity case. You can see how a lot of these tokens actually just aren't used in the sparse MoE. But here in the soft MoE, you're combining them, right? The router in sparse MoE layers and assigns individual input tokens to each of the available slots. The soft MoE, each slot is the result of a different weighted average of all the input tokens. Learning to make discrete assignments, so there's a learning process happening here, introduces several optimization and implementation issues that soft MoE sidesteps. So, whereas in the previous work, you had to learn this priority score, right? You had to actually, over time, learn the best way to score the different tokens such that you can route them effectively. Here, we're not going to have to do that. Okay, so Christopher H., what's average of which parts? So I think that's the whole point, is they're going to show us some way to come up with these weights, right? There's going to be some clever way to come up with these weights that you don't have to spend a bunch of time learning how to do it. What is the size of the patch? The size of the patch depends on the size of the vision transformer that you're using. Different vision transformers have a different number of patches. So the number here tells you the number of patches here. So 14, 14, 16. How is a slot defined? I think by a slot here, they basically mean the what actually gets fed into these MLPs. So basically they're constraining the size of the these experts, right, which are just fully connected neural nets, such that they can only take a certain amount of inputs, right? So here, in this high capacity case here, look at this expert. This expert has like 10 inputs. That would take a lot of compute, a lot of memory to have that kind of expert. So what if instead of that, we had an expert or 4 experts that each only had 4 inputs like that? So you see how each of those is called a slot, and that there's a limited amount of tokens. The experts can't actually consume the entire sequence of inputs. So bunch of pieces equals slot. Kind of. It's like the slot is how many things can actually go into the expert. There's a limited amount of slots per expert, and the total amount of tokens is higher than any one expert can consume. Caused by the discrete procedure and this core of sparse. Popular sparse MoE learns some router parameters. Learns some of the router parameters, and the source of the gradient is usually twofold. Post-multiplication of expert outputs with the selected routing scores and auxiliary losses that enforce some desired behavior and also depend on the routing scores. Okay, so basically you're learning this something that is improving the ability to assign scores, which then allow you to route them appropriately. And here, in this paper, the soft MoE, instead you're going to be learning these weights, which hopefully are more transferable. I'm not exactly sure why learning weights is going to be easier than learning these routing scores. To me, those are going to be very similar, but let's see. It has been observed that these mechanisms are often no better than random fixed routing. Interesting. So if you just randomly routed, you would basically get the same result. Soft MoE sidesteps as every routing is directly updated based on every single input token. Interesting. Soft routing can provide stability while training a router. Observe that during training, large fractions of input tokens can simultaneously change discrete routes through the network, leading to training challenges. Hard routing can be challenging with many experts, with most works training it with just a few dozen. We show that soft MoE scales to thousands of experts, and it is balanced by construction. Finally, there are no batch effects at inference where one input can affect routing due to limited expert capacity and hence prediction for other inputs. So kind of what they're saying here is that if you have a batch of inputs, right, because you have to decide where to route each token in each input, if there's many tokens that would all want to be assigned to the same expert, they're not going to get assigned to that expert because it's already full of other tokens. So let's say there's one expert that is very good at cats. If your batch has only one image of a cat, most of the tokens associated with that image of the cat are going to go to that same expert. But if you have a batch that's filled with images of cats, it's some of those aren't going to go to the right expert. They're going to be put into other experts. So that's kind of what the batch effects at inference mean. Okay, soft MoE. Is an expert a part of a large GPT, or are they smaller GPTs? You could think of them as fractional GPTs. They're basically like small independent GPTs, right? And the key word there is the independent. Where's the... I think it's actually in this picture here, right? VOE transformer block. Learnable router selects which experts, and these experts are independent, right? So they don't depend on each other's activations, which means that they can process slightly differently. And it's also this is kind of the same kind of intuition as to why ensemble models are better, right? Because it's kind of like diversity is strength, if you want to think of it another way to think about it, where it's like basically multiple models, even if they're smaller, their collective answer is actually generally better than one big model that answers basically entirely in sync, everything related to everything else. I don't know, that seemed like a kind of bad explanation, but they're not GPTs, but just FFNs. Yes. They're just this part here. They're just these fully connected layers here, right? So the mixture of experts, it's only here. It's only this fully connected part, right? Only this part, only the feed forward block. Okay. Soft MoE L16 beats VIT H14. And here, the reason that they think this is impressive is because H is, I think, is huge, and then L is large. I think this is supposed to be bigger than this one. Few shot and fine-tuning while requiring almost half the training time, but being 2 times faster at inference. Soft MoE B16 matches VIT H14 on few shot and fine-tuning and outperforms its upstream metrics after a comparable amount of training. Faster at inference. We train a contrastive model text tower against a frozen vision tower, showing that representations learned via soft routing preserves their benefits for image-text alignment. Okay, so here a contrastive model is basically a clip. So a clip has 2 encoders, right? The clip has one tower. You can think of it, isn't just another word to say basically a part of a neural net. So you can think of this bottom part here as an image tower, and there's an equivalent text tower. So here they're saying a frozen vision tower, even though this here is a convnet and they're referring to a vision transformer, and the text tower would also be a transformer. But interesting that you could use this for a contrastive model. So maybe the clip of the future is a sparse mixture of experts, or a soft mixture of experts. Okay. The soft MoE routing algorithm is depicted in figure 2. This is what we just looked at here. We denote the input tokens for one sequence by x. Okay, so input tokens are x, which is in the set of all real numbers, and dimensionality m by d. M is the number of tokens, so the length of your sequence. No, m is not the length of your sequence. M is the total number of tokens, or basically the dimensionality of your tokenizer, of your vocabulary, your dictionary, whatever you want to call it, right? The list of all your possible tokens. Each MoE layer uses a set of n expert functions. That's how many experts there's going to be applied on individual tokens, namely this. Okay, so f is the function that maps from D to D, so it doesn't change the dimension at all, right? The input is the same as the output, and there's n of these total experts. How useful are MoEs? Question. I think they're pretty useful based on kind of what they've said here. They kind of demonstrate, and they'll demonstrate later in the experiment section, that these MoEs are just as good in terms of performance, but way faster. So the whole point of MoEs is basically faster inference, faster training. Each expert will process P slots. So Christopher, this is where the number of slots P is coming from. And each slot has a corresponding d-dimensional vector of parameters. Okay. And I think the fact that it's the d-dimensional is not a coincidence there. We denote these parameters by phi. Let's make sure that's capital phi. Yeah, capital phi. Okay, just want to make sure. Phi in the set of real numbers of dimensionality d by n times p. N is the number of experts, and p is the number of slots. And the number of experts, n, and the number of slots, p, is just probably picked based on your hardware. So those are hyperparameters that you're picking depending on your hardware specs. Okay, the input slots x tilde n times p cross d, and are the result of convex combinations of all the m input tokens. So m possible input tokens, and you have a combination of all the input tokens. So kind of what's going on here, right? You have a combination of all these input tokens, some weighted combination. They're setting it up here, but they're gonna introduce weights at some point. Okay. So here D is what they're calling the dispatch weights, is the result of simply applying a softmax, and this equation is a softmax. So if you look at a softmax, the softmax is you take E as in like the exponential function, to the number over the sum of E of all parts of that number. So this is what a softmax is, right? So that's where this is coming from. They're just doing a softmax over this product of the parameters in the mixture of experts, or each expert has a set of parameters, and then X is the input over the columns of X and phi, X phi. As mentioned above, the corresponding expert function is applied on each slot, i.e. on rows, to obtain the output slots. All right, so these are your outputs. Y. Y tilde I is equal to the function of I over P, where these little, this L and this little backward L is basically rounding. So you're rounding to the split on P, right? So the P, which is the number of slots per expert, you're not gonna always be able to evenly divide the entire input, which is of dimension I, into these slots. So that's why this rounding is going on here. You're basically dividing it into slot chunks, but rounding so that they fit in that amount of things. The output tokens Y are computed as a convex combination of all n times P output slots Y tilde, whose weights are computed similarly as before. Okay, so now you have basically the exact same thing as before. This is the same thing as this up here, except now you have this C, right? And that C is the magical weights. C is the combined weights. So that's these numbers here. This is 0.09, 0.03, or 0.3, 0.4, 0.03. Those numbers are C here. And the interesting thing here is that C is coming from X and phi, right? So in their previous work, they had some expert router, right? So not here, but they had, give it a second here for the GIF to go through. So here in this GIF, they have this priority score. So there's some learnable set of parameters that is basically choosing which one of these tokens are the most relevant. But now what they're going to do is they're going to say, okay, well, we're instead going to give it a mixture or a weighted average, and the weights themselves are not parameters that we have to learn from some optimization process. These parameters are basically just based on the values themselves. So I used the inputs to determine the weights, basically, applying a softmax over all the rows. Following the usual design for sparse MoEs, we replace a subset of the transformers MLP blocks with soft MoE blocks. So no MoE is being applied to the attention blocks, which was, I think, another one of your questions, Christopher. It's only the multi-layer perceptron or the fully connected or the feed-forward blocks that are being replaced with these soft MoE blocks. In particular, we replace the second half of MLP blocks. The total number of slots is a key hyperparameter, right? Because the time complexity depends on the number of slots rather than on the number of experts. So the number of experts and the number of slots is just going to depend on your hardware. Are you doing this in a server rack with 8 GPUs? Are you doing this in 1 GPU at home? Are you doing this in a weird, like, distributed system that has different GPUs with different memory? So, like, all those different hardware considerations are eventually going to feed into what value you pick for the slots and the number of experts. Number of slots equals the input sequence length to match the flops of an equivalently dense transformer. Okay, so here we have the actual JAX implementation of a soft MoE layer. So what is JAX? JAX is basically like TensorFlow or like PyTorch. It's a code package, a code module, a Python library that allows you to basically do differentiable computation, which is basically I can basically write out all the math that I need, all the math that consists inside my neural net. I can write it out in Python code, and then the clever thing about JAX is that it basically compiles it into a computational graph that can run on a bunch of different hardware. So it can run on TPUs, it can run on NVIDIA GPUs, whatever you want, two NVIDIA GPUs, 4 TPUs. JAX will figure out how to basically compile it and then run it on that hardware in a relatively hands-off way where you don't need to know exactly the best way to implement it. JAX will do that for you, right? That's what the compilation is doing. Okay, so our soft MoE layer, right, of which there are a bunch of experts. There's however many experts was the number here that they were picking. N experts. It takes in X and it takes in Phi. And here we have JNP einsum. So taking a little divergence here because this is something kind of cool. So JNP is basically JAX NumPy. JAX gives you, there's a lot of functions in NumPy which basically JAX allows you to use in such a way that JAX also, whenever it's compiling this down into something that can run on hardware efficiently, it knows about this einsum, and because you've used JNP, it might compile it into something that's more efficient. So what the fuck is einsum, right? So now this is something that I actually asked ChatGPT before this. So an einsum, an Einstein summation, is a notation that basically simplifies expressions. So it's just a fancy way of writing down matrix multiplies, vector multiplies. Like, it's a fancy way of writing things basically because Einstein got tired of writing shit down. You know, like he lived in the era where you had to write things down with pencils and papers. So obviously you can see that he was just tired of multiplying tensors over and over again and writing down the full equation every time. So he came up with this kind of shorthand notation that allows you to basically write matrix multiplies, dot products, weird tensor multiplications in a way that's kind of more concise. So that's all that is. So for example, here is a dot product multiplication of two vectors in Einstein summation notation. So let's say if you had a dot b, each vector a and b has I indices. So ai bi, this is the Einstein summation notation. What it really means is that you're multiplying every element of A by every element of B and summing over all of those, right? So that's possibly the simplest possible Einstein summation notation. Here's a more complicated Einstein summation notation where let's say you had a matrix A and then a vector B. So if you wanted to perform this operation where you're summing from everything from j equals 1 to n, right, and then B has dimensionality j, there's j elements in B, and then A is a 2D matrix, so there's I elements, or I times j elements, right, the width and the height, I and j. And the way you would write this in Einstein summation notation is this, ij bj, right? So that's what's happening here. ij comma j to I comma I to none. So this is the Einstein summation notation for this simple dot product, and this here ij comma j arrow I is for this, right? So now what exactly is going on here? It's md comma dnp to mnp. So that means that the dimensionality of x is md, which is matching what we have here, right? Whereas x is here. Dimensionality of x is md, right? So it's a matrix that has m and d as the width and the height, right? And then the other element here, dnp, is the dimensionality of phi. So if we go up to phi, where's phi? Phi is here. It's d times n times p. So that also matches. Okay. So now we're basically multiplying this x, md, times this phi, this dnp, but the way that we multiply together, we want specific things to multiply with other specific things, right? So we specifically want to multiply these two things here that are of dimensionality d, these two dimensions that are noted with d, lowercase d. And we want the output to be m and p. So what does that actually mean? So I went and I actually got Copilot here, not Copilot, this is a code interpreter to actually give me the exact version of that. So this line right here, this JNP einsum MD, DNP to MNP, what it's really doing is this. It's basically saying you have some phi, you have some x. We're going to take the dot product of the d, the thing that has dimensionality d, the dimension with dimensionality d, and the phi dimension that also has that dimensionality d, right? You see how all elements, and then we're going to basically loop it over all p, over all n, over all m. So this line right here is just a fancy way of writing down this right here, right? Which is basically just your routing. And all of this comes from Einstein summation, which is basically a notation that was developed by Einstein because he was too lazy to write everything down. So one person in the early 1900s, because they were lazy and they didn't want to write down time and time again these tensor multiplications, they came up with this notation, and now this notation, you can use it so that you can write these matrix multiplies, these tensor multiplications, in a more efficient way. So rather than writing this here, you can basically write that. And there you go. That's a little side tangent on einsum and what that means. Okay. But once you have this einsum, then you're going to basically do the softmax, right? So this is what the softmax is here, the exponent to the thing, and then divided by the sum over the exponent to the thing, right? That's just the softmax here. Softmax function. There you go. Ooh. The input slots are weighted average of all the input tokens. So you see here is the C, so these are the weights. And then this is the actual, here, this D, dispatch weights. And then C, I guess C is also weights, so there's two different weights. There's dispatch weights and combined weights. So you get both of these weights, C and D. And then you multiply the input by the dispatch weights. And then apply the expert to each input slot. So then feed in XS into the expert. So you see here how we're enumerating the experts. So however many experts there are, we're each going to give them a slightly different slice of this XS, slightly different set of tokens. And then we're going to combine them back together into this YS. And then that YS gets multiplied by the C, which is the weights. So you're weighting it, sending it, routing it to each of the experts, and then weighting it again, weighted average. So that at the end, this Y here is the same as the X. The dimensionality of Y is basically the same as the dimensionality of X, which is what you wanted. You didn't want to mess with it. And that is what's going on. Pretty cool. Okay, so now that we kind of know what this is, let's go and see what are the properties of this. Why would you want to use this soft MoE over the sparse MoE? So can you repeat what phi is? Okay, so phi, let's go up here. We denote these parameters by phi. Each slot has a corresponding d-dimensional vector of parameters. Each expert will process p slots. So I think phi is the parameters for each expert. So it's basically, I don't know if that's parameters that you learn or whether that's parameters that are the parameters of the expert itself. Let's actually see if we can figure that out. Okay, so the soft MoE first computes scores or logits for every pair of inputs, tokens, and slots. Some based on learnable per slot parameters. Yeah, okay, so there is, this is the phis. Learnable per slot parameters. So for each slot, we're going to have some parameters that we learn. So this per slot learnable parameters, those are these phi's. Each slot has a corresponding vector of parameters. So each slot has some parameters that we're learning, and those parameters are going to impact. So maybe I was wrong here by assuming that everything would just be a function of the inputs. It's not just a function of the inputs. It's also, you also do have a set of parameters that you are learning. So I guess that's a little bit less hype. But those tokens determine these parameters. Those parameters are fed into this soft MoE weighting, which is the function that they have here. That function basically determines dispatch weights and combined weights. The dispatch weights are used to multiply the input such that you get slightly different weighted inputs. Each of those goes into the slots. Each of those goes into a specific expert. And then when it finally comes out, you combine them based on these combined weights, which are C. So this is D, this is C, this is phi, this is X, and this is Y. I'm not sure I understood that. Isn't that a kind of router again? Yeah, you're not wrong. It is basically a router, but each slot computes a linear, processes slots combined. Dash box represent learnable parameters. Let's see if they answer that question, because right now you are correct, Christopher. Right now it seems like there's per slot learnable parameters, which is analogous to the router that they're talking about here, right? This priority router. So something is happening here, because I thought the whole point was that you didn't have to do that. Here's the priority score. Maybe it's still learnable, but it's rather than being specific to one thing, it ends up being more transferable. Maybe that's kind of the secret, is that the learnable phi parameters are actually more transferable, more general, and they kind of work for more things. Maybe something like that. Let's keep going. At the core of all sparse MoE algorithms, there is an assignment problem between tokens and experts, and is usually a subject to some specific capacity imbalance. Different algorithms relax the problem or approximate the solution. Top K, or token choice, selects the top K scored experts for each token where there are slots available in such expert. Expert choice selects the top capacity scored tokens for each expert. Compute assignments. Nevertheless, virtually all these approaches are discrete in nature and thus non-differentiable. Oh, okay. Maybe this is what's going on. Okay, so maybe, so here they're talking about non-differentiable. So maybe what's happening is that all operations in soft MoE layers are continuous and fully differentiable. Rather than the hard assignments that sparse MoE methods typically use. Okay, all right, I think I understand this. All right, so here's the answer, Chris, is that even though you are learning parameters with these soft MoE layers, right, you are learning these extra parameters here, these phi parameters, which you do have to spend time to learn, and you're going to have to basically train your model and learn those over time. The thing is that you can learn them, right, is because this operation here, this vanilla routing, is discrete, right? So it's non-differentiable. At some point, I think this priority score is a non-differentiable operation, which means you can't push gradients through it, right? So I think that's the whole problem, is that here they figured out a way to do this routing in a way that's fully differentiable, which means that you'll be able to push gradients through it over the course of training and thus learn these parameters. That's kind of what it's sounding like over here. Virtually all of these are discrete and thus non-differentiable. All operations in soft MoE layers are continuous and fully differentiable. And this is because it uses soft assignments as opposed to hard assignments, where the hard assignment would be just picking something like an argmax, you know. But the soft assignment is you're just adding together and weighting. So you don't have that argmax anymore in there anymore. Therefore, it is differentiable. Inject linear combination of tokens instead of just token routed at least one slot per expert. Yeah. Priority routing. Routers would learn to discriminate and assign tokens. I think this is the problem. It's like, what is it like? This one makes it sound like it's also learning, right? Dropping the right tokens, priority routing. Learns to sort tokens according to an importance score. This still sounds like it's learning something as well. So how are they learning it here? We need a, I think there might be, is there a section here that talks about the difference between soft and sparse? Let's see. The classical routing mechanism mentioned above tends to suffer from issues such as token dropping. So classical routing mechanism, token dropping, which is I think what's going on here, right, where you're dropping the tokens here. So you're not actually performing any computation with these tokens, you're only performing computation with some tokens, and that's the dropping. Or expert unbalance. Some experts receive far more tokens. Unfortunately, performance can be severely impacted. Expert choice and token choice suffer from this. Soft MoEs are basically immune to token dropping and expert imbalance since every slot is filled with a weighted average of all tokens. All weights are in theory strictly positive thanks to the softmax. Okay, so obviously if you guys have ever seen the softmax function, so I've been showing you guys the equation for it, but the actual plot for it is like this, right? So the softmax basically takes any number that's negative infinity to infinity and it turns it into a number between 0 and 1. So you see how this actually has a softmax in it. So you see how if I click here, the value of this is 1.72, the value of this is negative 0.03, but when I come here, actually I would softmax over this, so maybe that's not the right example, but because we're feeding, oh my god, because we're feeding everything here through this softmax, like we're doing here, these are all positive weights. Strictly positive thanks to the softmax. Total number of slots is the main hyperparameter that determines the cost of a soft MoE layer. Every input applies such numbers of MLPs. The total number of experts is irrelevant. Few experts with many slots per expert or many experts with few slots per expert will have matching costs if the total number of slots is identical. Is that necessarily going to be the case? I feel like because of the way the hardware works, I bet you that one of these is better than the other. So the only constraint we must meet is the number of total slots has to be greater than or equal to the number of experts. Each expert must process at least one slot. The main advantage of soft MoE is completely avoiding sort or top K, which are also slow and typically not well suited. As a result, soft MoE is significantly faster than most sparse MoEs. Features of both sparse and dense. Sparsity comes from the fact that expert parameters are only applied to a subset of the input tokens. However, soft MoEs are not technically sparse since every slot is a weighted average of all input tokens. Every input token fractionally activates all the model parameters, and this is kind of where the fully differentiable comes in. All output tokens are fractionally dependent on all slots. Notice that soft MoEs are not dense MoEs where every expert processes all input tokens since every expert only processes a subset of the slots. I think the weird thing to me here is that this even works, right? Is that you can take tokens and just weigh them and combine them and the expert still works. Like that is a little weird to me, right? I can understand how if you give this expert like these 3 tokens here, which are like the nose of the bird and the tip of the bird, and you feed it, it kind of does something meaningful. But like, how come you can just combine these tokens, right? Like how is the combination of like the back of this bird's head with the front of this bird's beak, like how is that weighted combination meaningful at all? That's a little weird to me. It's kind of crazy that that even works. Under capacity constraints, all sparse MoE approaches route tokens in groups of a fixed size and enforce or encourage balance within the group. When groups contain tokens from different sequences or inputs, these tokens often compete against each other for available spots in the expert buffers. So this is kind of what they were talking about with the inter-batch dynamics, where depending on what else, what other inputs are in the batch with you, you're going to compete for a limited set of expert slots, which means that you now have a dependence on the output depending on what else is in the input. Right, so now this kind of feeds into what's happening here. So why is GPT-4 non-deterministic? It's non-deterministic because they're performing batched inference. And when they perform batched inference with a sparse MoE, it means that the input of your particular path, your particular input in the batch is dependent on the other inputs in the batch. So if you happen to ask a question and you're batched with a bunch of other people that ask the same question, there might be not enough slots in a specific expert to answer that specific, or to be routed, your question properly routed into the best expert, which then means that you're going to be routed into an expert that's not necessarily the best, and you're going to get a slightly different answer. How are the tokens chosen for each slot? So the tokens aren't chosen for each slot. Every slot receives a weighted combination of all tokens, and the weights are determined by these phis here, which are basically learned. So as you train this model, you learn these phis. Those phis are then multiplied by the inputs to create these weights here, the C and the D, and those weights are basically, specifically the dispatch weights, determine whether this slot receives one combination or a different combination. So every slot is receiving every token, but it's receiving a weighted combination of all tokens. So it's a little bit misleading because here it makes it seem like it's only receiving some tokens. You see how only some of these have numbers, but it's actually receiving every single token. It's just that the weighted combination has a bunch of, this might be 0.001 and 0.000001 or something like that. But they do say here that every slot is filled with a weighted average of all tokens. So there is a path, there is a gradient path, right, for every single token through an expert. Yeah, it's kind of like attention. Yeah, you are correct there, Christopher, where it's like kind of the same idea of attention, right? Where an attention mechanism, the whole kind of like idea behind the attention mechanism is that like, hey, why don't we take every part of the input and give it a way to communicate with every other part of the input, right? So that's kind of like the core intuition in attention mechanism as well, where it's like this idea that like everything should have a path through everything else. Like you don't want to kind of like hard route. You want to do this soft routing where there is a way for one token to pay attention to a different token, or in this case, for every expert to have a little piece, a little bit of the information from every single token. It's kind of a cool idea, Chris. As a consequence, the model is no longer deterministic at the sequence level, but only at the batch level. Right? And because when you're doing inference with GPT-4, you're getting batched together with a bunch of other random people that happen to put their prompt at the same time that you put your prompt. So as some input sequences may affect the final prediction from other inputs. Models using larger groups tend to provide more freedom to the routing algorithm and usually perform better, where their computational cost is also higher. When groups contain tokens from a single sequence, the model is forced to use every expert on every input sequence. This may lead to more generalist experts. Moreover, changing the group size between training and inference can be problematic due to the potential distribution shift in token to expert assignments. Yeah, so this is interesting, where you've now learned these parameters, these phis, right? This phi parameter here. But that phi parameter has learned a specific, has learned how to choose the right slot depending on a batch of data, right? So that these per slot learnable parameters here are, I don't want to say overfit, but they're certainly specific to the distribution of training batches that you're feeding. So if the distribution of the batches that you're seeing during inference are very different, then maybe these per slot learnable parameters are no longer going to be as good, right? Maybe they're actually going to be, it's now they're trying to perform outside of the distribution that they're trained on. So that's actually kind of clever, where you want to actually learn these phis, these per slot learnable parameters from batches of data that are ideally sampled from the actual inference batches that you would receive. So it's kind of clever to think about. Okay. Soft MoE gracefully sidesteps all these challenges. Since it combines all tokens in each input sequence, we just set a group size to be a single sequence. Every expert does handle tokens from every input, maybe somewhat limiting the amount of high-level specialization. Yet this also implies that it is per example deterministic and fast, while typical instances of sparse MoE are not. I don't know if I necessarily agree with this, because I still feel like even though it is per example deterministic, because now every single slot is a weighted combination of all tokens, and you're no longer doing this kind of sparse routing where some of the tokens are getting missed out. I think the problem is that the distribution, the routing, or in this case the weighting of those tokens, is still being done based on the assumption that the batch at inference is going to be the same as the batch at training. So I feel like there's a kind of like a little bit of, you're going to have a little bit of an out of distribution effect here, depending on how similar your training batches are to your inference batches. Okay. Implementation. Time complexity. Okay. Assume the per token cost of a single expert function is O of k. Okay, so the time complexity, big O notation here, this is, if you guys have ever done leet code problems, is basically a way of saying how much time is it going to take to run this algorithm, and then how much memory is it going to take to run this algorithm, right? So certain algorithms take a lot of memory and maybe less time. Some algorithms take more time and not as much memory. But here they're basically saying, okay, see, the amount of time that it's going to take to run this expert is dependent on the number of tokens, and that's k. So it's linear with respect to the tokens. The time complexity of a soft MoE layer is then this, where now they're introducing these other dimensions here, MND, MNPD, and then NPK, but it's still linear with respect to the tokens. By choosing P equals O of M over N slots per expert, the number of tokens over the number of experts. So this is kind of how they're going to pick the hyperparameter P. The cost reduces to M squared D plus MK. So generally, as soon as you see squared terms or cube terms inside this big O notation like that, that's generally not a good thing, right? You want your time complexity to be ideally linear or sublinear, depending on whatever the crap is in here. But as soon as you see squareds, it's no good. That means that if M increases, the time complexity increases squared of that. Joseph Enochs. So multi-head attention, which is fully connected, passes through the FFN with this new softmax. Same thing happens when we add in the masked attention elements. So you're talking about the masking going on here. I think the masking here is so that the decoder can't pay attention to the things beyond the current position. I'm not sure what your question is. Sorry, Joseph. Given that each expert function has its own set of parameters, increasing the number of experts n and scaling p allows us to increase the total number of parameters without any impact on the time complexity. Moreover, the cost of applying an expert is large. The mk term dominates over m squared d. Oh, interesting. So even though this has a squared in here, if the number of experts is large, then this mk dominates. And the overall cost of a soft MoE layer becomes comparable to that of applying a single expert on all input tokens. Finally, even when m squared d is not dominated, this is the same as single-headed self-attention cost. Thus does not become a bottleneck in the transformer models. Okay, so kind of what they're talking about here is that in transformer models, the bottleneck is not this feed forward here. The bottleneck is this multi-head attention. This multi-head attention mechanism is squared in the with respect to the length of the input sequence, because you basically have to take every part of this input sequence and basically make this square where literally every part let me actually pull up a picture of that. Tension map transformer. Yeah, like this. Open image in new tab. So these are two slightly different types of attention. This is a local attention where you're masking out the part that isn't relevant, but in full vanilla self-attention like this right here, the length of these two squares is going to be the biggest computation that you're going to do in your transformer. The most memory intensive thing, the most time intensive thing you're going to be doing in these transformers is this attention mechanism here. So they're basically saying that this mixture of experts, right, is not going to be the worst thing. So therefore it's not going to be your bottleneck. So you're totally fine. Left side happens first with encoding and no masking, and then masking. Then those are combined above in the FFN on the right. You're talking about this? Yeah, this is the encoder, or the encoder. This is the decoder. So encoder happens first, then decoding. There's no masking on the encoder. That's correct. And then the masking happens on the decoder. That's also correct. That's what this masked here is. Those are combined above in the FFN on the right. So here. Yeah, okay. So this is the masked attention. That masked attention is then fed into this cross attention here. This cross attention is not a self-attention, right, where it's not attending to itself here, as you see with these three arrows or these three arrows here. These are self-attention. This one is now cross attention between what's coming out of here of the encoder and what's coming here out of the lower parts of the decoder. And then that is what's being fed here into this feed forward, and this is probably where the mixture of experts is being applied. I agree with that, Joseph. Okay, in transformer, MoE layers are typically used to replace the feed-forward layers in each encoder block. Okay, so maybe not. So in transformer, MoE layers are typically used to replace the feed-forward in each encoder. So it actually sounds like they're using them here. I don't know if they're using them here. It kind of sounds like if it works here, then why wouldn't it work here, right? We'll see. Using pre-normalization as most transformer architectures. So pre-normalization just means that you're taking this added norm here, and then you're having one here, which is what they show you here. So here's pre-normalization. Here's another normalization. The inputs to the MoE layer are layer normalized. This causes stability issues when scaling the model dimension d, since the softmax approaches a one-hot vector as d goes to infinity. Okay. Thus, line 3 of algorithm 1, we replace x and phi with L2 normalize x and scale times L2 normalize phi. Right, so in their algorithm here, the input x is just normalized. That's kind of what they're saying there, right? Is that the input here is normalized, and the normalization is just this, L2 normalize. replace x and phi with that. They also normalize the phi, whereas scale is a trainable scalar, and L2 normalized normalizes the corresponding axis to have unit L2 norm as algorithm 2 shows. Jack's implementation of the L2 normalization used in soft MoE layers. So here they would feed both the x, as in capital X, as in the input, and phi, as in the learned per slot weights. For relatively small values of d, the model dimension used for VIT models up to VITH that use d less than 1280, the normalization has little impact on the model's quality. However, with the proposed normalization in the soft MoE layer, we can eventually make the model's dimension bigger and or increase the learning rate. Okay, so I think what they're going to do here, kind of what they're setting up, is they're probably going to... Actually, let me just keep going. Let me just keep going before I kind of start theorizing about things I haven't read yet. So, I mean, just as a side note, like, I don't read these papers before I do these streams, and I think the reason for that is that I wanted to kind of make sure that people see me struggle, you know, and people see me try to understand things, and people see me whenever I like go off on a tangent, I'll learn something. And like, the reason I'm doing that is because I think it's like that's how you actually learn things. You know, it's like I'm curious to see how people actually solve problems. I don't care about once they've actually solved it, they explain it to me in 20 minutes. That's, you know, I want to see the process. So if you guys enjoy that, that would be great, you know, and I feel like that's why you guys watch the channel, but maybe you guys don't enjoy that. You'd rather just see me read the paper and then give you a 30-minute summary. So if that's more what you guys want, let me know. Just got on the stream. How's it going, Kalina? If MOEs are FFN layers, that should be equivalent to saying FFNs are transformers brains. Huh? Kind of what we're realizing is that these mixtures, especially these weighted averages of experts, the soft MoE as they're calling it, is kind of a weird alternate type of attention mechanism. It's very similar, where you're basically coming up with these weights, and those weights are used to basically route, or in this case they're calling it distribute, these distribution weights. Right? Like, what is the difference between dispatch weights and query values, query matrix, the key matrix, right? It's like they're not obviously not the same, but it's like there's kind of an analogous thing there, right? We do enjoy your struggle more. I appreciate it. Probably they said it only replaced feed-forward layers and encoder block because the VIT is encoder only. Oh shit, I think you're right, Ed. Yeah, I think you're correct. I think that here they're only talking about vision transformers. So yeah, I forgot that this paper is only vision transformers, even though you could apply this to natural language as well and text. But here, specifically for a vision transformer, they're only putting it here in the encoder because at the end of the day, they're just going to take this vision transformer and probably do like an ImageNet or some kind of task to determine the quality. Okay. Distributed model. When the number of experts, it's not possible to fit the entire model on a memory on a single device. I feel the pain, especially during training or when using MOEs on top of a large model backbone. In these cases, we employ the standard techniques to distribute the model across many devices. So model parallelism. And other works training large MoE models. Distributing the model typically adds to an overhead in the cost of the model, which is not captured by the time complexity based on flops we derived above. Yeah, and I think this is kind of what I was getting at before, where it's like choosing the right value for these number of experts and then the number of slots. It's gonna be really annoying and really complicated because it's gonna depend on like so many things in your hardware and like even within the hardware, right? It's not just the GPUs that you're using, but like what is the interconnects that you're using, right? Different interconnects, different overhead, different choices for the hyperparameters. So picking the right hyperparameters Huge pain. In order to account for this difference, all of our experiments, we measure only the flops, but also the wall clock time and TPU v3 chip hours. Okay, so obviously this being a Google Brain paper, they're going to be doing, they're going to be using TPUs, which are Google's GPUs. I appreciate that all of you guys want to see me struggle, you know? I want to see myself struggle. You know, if I'm not struggling, I'm not growing. Your loss function has to have some value in order for learning to occur. If your loss function is just 0, then your gradients are going to be nothing. Many existing works merge, mix, or fuse input tokens to reduce the input sequence length. And this is probably what Claude is doing, right? Like Claude, whenever they advertised it, they're talking about how like, oh, it has like a bajillion input tokens, right? But the reality is that it's not actually processing every single one of those tokens. They probably just have their own weird way of merging, mixing, and fusing the tokens in such a way that it reduces the total sequence length. And maybe it's some weird mixture of experts thing as well. Typically using attention like weighted averages with fixed keys to try to alleviate the quadratic cost of self-attention with respect to the sequence length. This is legit the deepest ML thing I've ever heard. Sigma grind set. Sigma grind set is kind of like a Gen Z term, right? Although our dispatch and combined weights are computed in a similar fashion with these approaches, our goal is not to reduce the sequence length. We actually recover the original sequence length after weighted the expert's output and combined weights at the end of each soft MoE layer. Yeah, so the problem is that like they make it sound like, oh, it's magical and we don't have to we can deal with any sequence length. But the answer is there is a dependence here on the sequence length, right? These dispatch and combined weights are going to depend on that, right? Because also these phi's are also going to depend on that. So like there is going to be more, the dimensionality of these dispatch and combined weights is going to grow as you increase the length of the sequence. So it's not going to be as bad as the quadratic self-attention, but there's still a little bit of a dependence there. If you had 10 bajillion length input sequence, you would eventually need a huge amount of weights to combine them, and even that, the process of combining all those weights and creating this kind of like weighted average token would get out of hand. Multi-headed attention also shows some similarities with soft MoE. There you go, Christopher. They came to the same conclusion that you did, that like, wait a second, this soft MoE kind of sounds a lot like attention. Beyond the use of softmax and a weighted average, the H different heads can be interpreted as different linear experts. The distinction is that if M is the sequence length and each input token has dimensionality D, each of the H heads processes M vectors of size D over H. The M resulting vectors are combined using different weights for each of the M prime output tokens, i.e. the attention weights, on each head independently, and then the resulting D over H dimensional vectors from each head are concatenating into one dimension D. Our experts are nonlinear and combine vectors of size D at the input and output of such experts. Oh shit. Okay, so basically what they're saying, the key difference here between multi-headed attention and soft MoE is that the head, each in this multi-headed attention, the heads are processing a smaller, or processing a subset of the total amount of input, versus in this soft mixture of experts, every expert receives every single, or has a path to every single part of the input sequence because it's all weighted together. Yeah, each head independently, and then the resulting vectors are concatenated into one output of dimension D. Versus here, you're now combining all of them at the input and then at the output with the two different weights for each set. Or one weight for the input, which is the dispatch weight, or dispatch weights, and then the output is I keep forgetting the name of these things. What is it? Dispatch weights and combine weights. Kind of cool. I wonder what would happen if you just replaced everything with these. Could you just have like a model architectures that just like 50 different soft MoE blocks just on top of each other? Like, would that work? Is this the new transformer? Is this what's about to happen? There are also connections with other MoE works that use a weighted combination of the experts rather than doing a sparse routing of examples. MoE is all you need. Heard it here first. So sometimes one thing you can do is you can search up these people. So let's search up this guy, Johan Puskgiver. So you search up these dudes. You go to their GitHubs. And you see what they're working. Okay, so this guy doesn't push a ton of code, but the last thing that he pushed was this: Google Research vMoE, vision with sparse mixture of experts. I think that's what this is, sparse mixture of experts. But sometimes you can go on people's GitHubs like that, and you can see what they're working on now, because the papers that come out, the papers are delayed, right? So like the paper is not what people are working on now; it's what they worked on like 3 months ago, 2 months ago, something like that. So sometimes you can go on GitHubs and get a sneak peek about what they're working on today, but I don't know, didn't find it. These approaches are also fully differentiable, right? So there's a path for the gradient to travel through every single expert and to every single token. And although they can have a much higher cost, since one, they must average the parameters of all the experts, which can become a time and a memory bottleneck when experts with many parameters are used, they cannot take advantage of vectorized operations as broadly as soft MoEs, since every input uses a different weighted combination of the parameters. It's kind of hard because it's like depending on the optimizer, like I could see how this is gonna become a huge tangle of shit. Because there's the complex, even just performing inference, there's like a weird relationship between the hardware that you're using and like what size, how many experts should you have, what should be the number of slots, what should be the number of attention heads. Like there's so many different, there's a really weird relationship there. And then if you add to that training on top of that, so now you have to think about, okay, well, maybe my model fits perfectly for inference, but now if I have to do training, like, and I have to keep the optimizer state somewhere. Now it's even more complicated. So, I don't know, that's some fucking dark art shit in order to figure out what the hyperparameters to use in order to optimally train a soft mixture of experts on a TPU v3 chip. Jesus. Okay, current limitations. One of the key aspects of soft MoE consists in smartly merging all the tokens in the input. This makes use of the soft MoEs and autoregressive decoders difficult, since causality between past and future tokens has also to be preserved during training. So autoregressive decoders is this part here. This is the decoder. This is the encoder. And causality between past and future tokens has to be preserved during training. So the causal mask using attention layers could be used. One could be careful not to introduce any correlation between tokens and slot indices, since this would bias which token indices each expert is trained on. The use of soft MoE and autoregressive decoders is a promising research avenue we leave for future work. Okay, so I think this answers, I forget who asked this question, but this MoE is only here in the encoder. You could not do it here, because the problem is that if you were to try to do it here, you would know what the other tokens are, right? So when you're doing a decoder, the decoder has a mask, and the mask prevents future things from impacting the current thing, right? So the decoder is basically trying to predict every token one at a time, right? So it's saying, okay, given these first 10 tokens, what is the 11th token? But in the attention mechanism, there's a mask that prevents the attention mechanism from seeing the value of the future token. So it has to basically regress the next token based on only what it's seen beforehand, only the first part of the sentence, right? But if you're using this mixture of experts, the mixture of experts works by basically giving you a weighted combination of all tokens. So if you can't do that in a decoder, because then if you were giving it a weighted combination of all tokens, that's basically now you're giving the attention mechanism, the decoder, a way for information from future tokens to come in. So now it's no longer a decoder in the sense that it's only paying attention to the previous things. Now it has, through these different experts and through this weighted average of all tokens, it has a way for that information from future tokens to leak in. So because of that, you could not just naively do soft MoE for the decoder part of a transformer. So you could probably do some kind of masking, right? You could probably, as they say here, basically do the same thing that you do in the transformer or in the this part here where you mask it. You could probably do something similar. You could do a masked soft MoE. So there's a future research paper if one of you guys are interested in masked MoEs for transformer decoders. But they don't do that in this paper. They're only interested in the vision transformer, which they're using as an encoder. So they're really only having this left side here. They're going to publish the code in the same GitHub. So you're saying that all the code is going to come here, probably. This is not an officially supported Google product. Okay. Lazy experts and memory consumption. We extensively show in section 3 that one slot per expert tends to be the optimal choice. In other words, rather than feeding one expert with 2 slots or mixes of tokens, it is more effective from a performance standpoint to use 2 experts with 1 slot each. We hypothesize same expert slots tend to somewhat align and provide small informational gains, and single experts may lack the flexibility to accommodate very different slot projections. Soft MoE tends to average or leverage a large number of experts, and while this cost is still similar, the memory requirements in the model can grow large. Okay, so in the picture here, they have these slots, and they show multiple slots going into the same expert. But they say that actually the better way to do it is just to have 1 slot per expert, right? And it kind of like there's going to be dynamics here, right? Because your learnable parameters phi here are per slot. So these phis that you're learning, which are basically telling you the best way of routing, or in this particular way, the best way of combining these tokens, right? These weights. If you have 1 slot per expert, that means that these per slot learnable parameters they're effectively per expert learnable parameters. So they kind of learn the intricacies of specific experts. But if you have multiple slots going into one expert, then the slots might end up kind of overfitting to other specific concepts. So I guess there's some dynamics there, and then it makes it the way that they wrote this, it sounds like there's also trade-offs in terms of the actual memory and time complexity as well. Same expert slots tend to somewhat align and provide small informational gains. Yeah, so if you have multiple slots that are going to the same expert, they're going to basically end up aligning, aka they're going to basically end up giving the same or choosing the same weights and providing basically the same shit into the expert, which means that you now have 2 slots and you're learning per slot parameters for each one, but each of those 2 slots might as well be the same slot. Basically, they provide a very small informational gain. It's not like they're providing very big informational gain, so maybe you could save on some memory by basically use 1 slot per expert, or even 1 slot for 2 experts. Okay. All right, so now that we've gone through all of Soft MoEs, they're basically going to prove that it's actually worth doing this. And the way that they're going to prove it is with image classification. So image classification is basically this. This is image classification. So this is a ConvNet. I showed it earlier in the stream, but basically it shows you what all the different neurons in a ConvNet are doing. This is a really old model at this point, very old ConvNet, and it's classifying what you write here as one of the digits from 0 to 9, right? So you can see if I do this, and then if I ever so slightly start changing this, it starts to think, okay, now it's for sure a 9. If I delete this, it thinks it's a 9. If I delete that, now it thinks it's maybe a 7 or a 9. If I delete this, now it thinks it's still a 9. Let's see if we can get it to do a 1. There you go, now it's a 1. So that's image classification. We present 3 types of experiments. Training Pareto frontier. First, in section 3.3, we systematically compare dense VIT models, so VIT models that are fully dense, right? Every path is calculated at the small, base, large, and huge sizes, so different sizes of VIT, so VIT-S, VIT-B, VIT-L, and VIT-H, with their sparse counterparts based on the most common routing techniques. Okay, so they're going to compare to a dense VIT, then they're going to compare to 2 different MoE variants, token choice and expert choice, and then they're going to compare to their own soft MoE. So those are going to be the 4 different things that we compare here. We studied the training flops versus performance and training time versus performance plots to conclude that soft MoE dominates all other approaches. Kind of interesting that they use the word dominate here. Like, you know, you could have used the word outperform, and that would have been more vanilla, more science, but the word dominate kind of inspires intensity. Like, I don't know why they chose that word. That's kind of a weird word to pick. In section 3.4, we present longer training runs, overtraining. Okay, so overfitting. Relative to VIT, soft MoE brings large improvements in terms of inference speed and absolute performance. Yeah. Right? Rather than saying our work achieves state of the art, you say our work dominates all previous work. Okay. And then model ablations. We investigate some of the central aspects of soft MoE routing and compare their behavior with other routing algorithms. We present the optimal configurations and the source of the improvement benefits. Okay, so these are the different experiments they're going to do. Pre-train our models on JFT4B. Fuck is this? JFT4B. JFT4B dataset. Let's see what it looks like. Is an internal Google dataset, consists of 3 billion images. In other words, data are associated as noisy. Can I get this? Plan to release the weights on JFT300. This is our internal data set, and we are not allowed to release these weights. Okay, so every time you sent a picture to someone on Google Gmail, or anytime you have a Google Hangouts call, they're basically secretly taking pictures of you, and that internal data set is what they're going to be testing on. A proprietary data set whose latest version contains more than 4 billion images, covering more than 29,000 classes. Okay, so pretty big data set, to be honest. That's a lot. In the context of multi-criteria analysis, dominates means specifically outperforms in every metric. Outperform could be better in a few metrics, worse in another. Okay. Interesting. I did not know that. So apparently there is a formal definition for dominates. It basically means that it outperforms in every metric. Thanks for that, Joao. We typically evaluate on 2 metrics: upstream validation precision at 1 on JFT4B and ImageNet 10 shot accuracy. Okay, so they're training on this JFT4B, but then they're evaluating on basically ImageNet, which I guess is like a way to kind of test the ability of the model to transfer. And the latter is computed by freezing the model weights and replacing the head with a new one. So freezing the model weights and replacing the head with a new one. So back to our little visualization, that would be like keeping everything underneath here, keeping this entire part here, and then just throwing away this part here, which is the model head, this fully connected head. Trained on a dataset containing 10 images per class. So this is where the 10 shot is coming from. So they basically take their vision transformer, which has been pre-trained on this JFT4B. Then they cut off the head, train it for a little bit longer on ImageNet 1K, and then see how it performs. We provide the accuracy on the validation set of ImageNet 1K after fine-tuning on the training set of ImageNet 1K. Okay. We compare the following popular MoE algorithms: Token's Choice and Expert's Choice. Every token selects the top K experts with the highest routing score. Blah, blah, blah. Batch priority routing. Improves model performance, and especially in the case. Okay, so some version where basically you're picking out of the top K experts. Maybe it's kind of this priority routing crap. Priority scorer. Expert's choice. Experts select the top C tokens in terms of routing scores, and then you have all these other hyperparameters C, such as buffer size, blah, blah, blah. It's common some tokens are simultaneously selected, whereas some tokens are not selected at all. So this is the non-differentiable. Why expert's choice sucks. How do they perform on from a hallucination standout? Is it better or more or less the same? I don't know. Yeah, so this is for a vision encoder only, so hallucination is not going to come in here, right? What they're basically using this for is they're using this to take an image, encode it, and then use those features that what's coming out of the image model, and then saying, okay, is this useful for ImageNet 1K classification? But I think your question is maybe more interesting, which is, would a MoE, a soft MoE transformer be better at hallucinations or less good at hallucinations, right? I don't know. It's hard to say, right? And maybe if you were using here where they say the soft is an autoregressive decoders is a promising research avenue that we leave for future works, you should carry out that experiment. So if you're going to be doing that, if you want to do that research and you want to basically do a soft MoE for the decoder part of a transformer and actually generate outputs and put in a little mask in here so that you can actually do the autoregressive decoding, maybe it's the case that it's less hallucinations, or maybe it gives you more hallucinations. I don't know. It's I think it's up to you, Mabong Geni, to do that research and let us know. Okay, training Pareto optimal models. So you have all these different sizes of vision transformers here, and their sparse counterparts. We consider 3 routing algorithms for the sparse models. Here are the 3 different routers. So soft MoE is the one in this paper, and then token choice and expert choice are the 2 that they described here. We train several model variants, K, C, and number of experts. So they're going to try different values for the hyperparameters. These KC are the hyperparameters for the experts here, or the MoE variants here. They train 106 models. Only in Google, with Google training budgets, can you train 106 models on a 4 billion image data set. Models are trained for 300K steps with a batch size of 4096 in all cases, and inverse square root learning rate decay. So little learning rate schedule for you guys as well. Figure 3A and 3B show the results for models in each class that lie on their respective training cost - performance Pareto frontiers. Soft MoE strongly outperforms dense and other sparse approaches for any given flops or time budget. Okay. So here we go. Soft MoE is going to be the blue dots. Expert's choice and tokens choice, which are other MoE algorithms, are going to be this orange and green. I think the size of the dot is going to be the size of the model. So obviously a little tiny vision transformer is not going to perform as well on precision at 1 or on ImageNet 10 accuracy. So obviously the model size matters. So the big models are going to be the best. That's why the big circles are at the top and the small circles are at the bottom. Here in the x-axis you have total training. So 2 different ways you could think of it in wall clock time. So how long in the real world did it actually take you to run this, versus flops, which is a more quantitative measure of how much training was actually done. You see these are log plots, so 10 to the first, second, third power. So the you can see it a little bit cleaner. That's why people use these log plots like that. What else? What we're seeing here is that the soft MoE is always at the top, so it always seems to have better performance, better accuracy and precision. Here, precision at 1 and then accuracy for the same size of model and the same amount of training. So what that's letting you know is that dense here just means basically vanilla. You're not doing any of this mixture of experts. You're just kind of training the vision transformer as is and then using all of the weights at runtime, at inference. And yeah, that's the this is the what you want to see here is that this blue dot is higher than the orange, green, or red. This blue dot higher than the orange, green, or red. Down here, this blue dot higher than the orange, green, or red. So pretty much regardless of the model size, regardless of whether you're doing full training or whether you're doing this pre-training and then fine-tuning, which is what this is here, this transfer kind of task, in pretty much any metric you can think of, the soft MoE performs better, which, according to the definition given to us by Joao of domination, means that soft MoE is dominating expert's choice, token's choice, and dense. So there we go. Ensembles of experts show softmax may be a way to help with hallucination, which ensembles GPTs and feed forward with softmax to weigh GPT outputs. I wonder how GPT-4 does the masking part for the decoder. Maybe we can use the same concept for vision MoE. Yeah, I mean, it's kind of weird to think about how like they might actually have that, right? So we sit here and in this Google paper, they say, hey, maybe we should research this. And it might just be the case that people at OpenAI did do that. They did go and they did research this and they did come to the conclusion of how to implement soft MoE for a transformer decoder. And then they have that, but rather than publishing it and being OpenAI, they decided to keep that secret. So they know exactly how to mask this feed forward here in the decoder for a soft MoE, but they're not going to tell you. Because fuck you. You know, how dare you try to learn more. In addition to shorter runs and ablations, we train a number of models for much longer to test capabilities at larger computational scales. We trained VIT and soft MoE at different sizes, kept training on some of the previous soft and beyond the optimal points suggested by standard dense scaling laws. So what they mean here is that how long you train a model, there's some scaling law which says, okay, if you have this size of a model, you should train it for this long, right? And loss curve for models. Most, whenever you're actually training a model, right, the behavior is going to look like this. This is like the loss for some model that you're training on something, and you can see how over time the loss decreases quickly, but then it starts to like kind of like tail off, right? And the training that you paid for here, totally worth it because it got way better. But the training that you paid for here, not really worth it because it just got barely better. And there's kind of a scaling law. I would call it more a scaling hypothesis or a scaling heuristic, I don't know, that says, okay, you should probably stop training once you reach this point. But I don't know if law is necessarily the right way. Law is too intense for me. Sparse models can leverage the extra capacity to steadily improve their performance. Okay, so not only is the soft MoE better at the same amount of training, but it actually, you can train them more, which is kind of great. Pretty much better on every metric. This should be much more difficult to train with something like LoRa because each expert would need its own LoRa. Yes. That if you wanted to put a LoRa, a low rank adapter, I don't know what the thing is, but if you wanted to put one on these MoEs, you would probably need to put one on each one. You can put LoRa's on any part of any model, right? So you could put LoRa's on these phis. It could be the case. You could just put it on here on this per slot parameters, and then maybe you can get the behavior that you want. I don't know. Train a number of soft MoEs, allowing for considerable comparable setting Replace the last half of the blocks with soft MoE layers. Last half of the blocks with soft MoE layers. Using 1 slot per expert. Train models ranging from 1 billion to 54 billion. Parameters. Large soft MoE models incur in small wall clock time overhead compared to their dense due to the extra data transfers required by model parallelism. Ruh-roh, that's not good. Shows the JFT4B precision, ImageNet 10-shot accuracy, and ImageNet fine-tuning accuracy. Table 2 contains results. Figure 19 shows performance versus core hours. Soft MoE models widely outperform vision transformer models for a given compute budget. Let's research it and train 106 models. Yeah, I don't have the GPU budget to do that. I'm actually GPU poor. I don't have a single A100 in this house. Certainly don't have any H100s. Encouraged by the fact that soft MoE with smaller backbones can match the quality of larger vision transformers, we continue training the small backbones to obtain models of higher quality at very low inference costs. Even after overtraining, the overall training time with respect to larger VIT models is comparable. We observed that longer cooldowns, paired when the learning rate is increased linearly to 0, work well for soft MoE. So here they're talking about the learning rate scheduling. So it seems that the soft MoE, not only can you train it for longer, but also the learning rate schedule should probably be different. So this to me means that you could probably come up with a new type of learning rate schedule that is optimal for soft MoE. So that's a whole other area of research as well, right? The interaction between the learning rate schedule, even just the paper that we read last week where the batch size, there was like basically extra optimizer hyperparameters, and they came up with these like scaling laws for picking the right optimizer hyperparameters depending on the batch size, and there's probably all kinds of similar relationships you could come up with for the hyperparameters of the soft MoE. So many cool things to explore. Soft MoE B16 trained for 1K TPU v3 days outperforms VITH trained on similar budget, being 10 times cheaper at inference and doubles the training budget. Beats all models substantially. Yeah, so it's pretty much, it seems like it's like a no-brainer. It's just like better in every single way. It's faster, it's cheaper, you can train it for longer. Train for 4 million steps, similar training costs. So here you have ImageNet 10-shot accuracy, ImageNet fine-tuning accuracy. So the difference here is they basically, the 10-shot is they cut off the model head and then put a new model head and then basically only push gradients into that model head. Versus fine-tuning accuracy, here they're actually fully fine-tuning. So they're basically pushing gradients from ImageNet all the way through the entire model, right? So that's the difference between this 10-shot accuracy and this fine-tune accuracy, but it doesn't even matter because the soft MoE is better in all of them, right? So you could have had like a weird, interesting result where the soft MoE is good for this 10-shot style of fine-tuning, or maybe it's not as good for full fine-tuning. Like there could have been a more nuanced relationship here, but there isn't. Basically, no matter how they do the pre-training fine-tuning, pre-training, one-shot, pre-training, zero-shot, like it seems like the soft MoE basically just wins every time at different sizes and for everything. Training and fine-tuning, this is basically just the thing up here, but in text form. For you text enthusiasts, are you a table enthusiast or are you a plot enthusiast? I'm generally more of a plot enthusiast. I love plots. I think this is I'd much rather have the data presented like this than like this. But if you're a little stickler and you love to see the exact final numbers, to the full precision, then maybe you're more of a table enthusiast. Plot gang, yeah, I'm definitely on plot gang. Okay, soft MoE ablations. Okay, so now they're going to do some ablations. Ablations are basically experiments where you try to take your approach and then kind of like pick apart all the different parts of it and then see which of these parts are more important in determining the final result. So here they're going to explore the different hyperparameters, such as number of slots, number of experts. So 1 or 2 slots per expert. I think they said that they ended up picking 1 slot per expert. Bring him over. Okay. And same number of experts works best when using 1 slot per expert. To show this, we increase the number of experts, train the same amount of time, and find best performing model. Okay, soft MoE optimized for inference. Quality of JFT achieve different models with different training and inference cost. Soft MoE long versus soft MoE. So what does the long refer to? Where is that? Dark blue curves correspond to soft MoE trained for additional steps. Okay, so the long means the ones that they kind of overtrained. You would possibly use the word overfit here, but it's not actually overfitting. You can keep training and it doesn't overfit, right? That's kind of what they're showing you here, is that if it were to overfit, then this dark blue line would actually start to go down, right? Where basically you would see that even though you trained it longer, it would actually perform worse. But the fact that it doesn't, and that the dark blue line, which you trained for longer, is above this dotted blue line, which is trained for shorter amount of times, means that you were able to train it longer and it was able to find even better model. Yeah, so I mean, this is pretty next level, because it's like the blue line is always higher, except for here. Here the blue line is not higher. But it is, because this dot corresponds to this dot corresponds to this dot, and this dot corresponds to this dot. So it's still higher, it's just not as intense, not as good. But this is crazy, because here they're different sizes, right? So the dots here represent different sizes of vision transformers, and you see how the very small vision transformer here, VITS, is already performing just as good as the VITL. Look at that. So you can use a smaller model, and all you do is just train it for longer, and it'll perform just as good as a big model trained for less time. So soft MoE just absolutely dominating over here. Maybe they weren't wrong by using the word dominate, because it's really is dominating. It just wins at everything. Following recipe, dark blue corresponds. Number of experts. We apply soft at a given architecture. One must decide how many experts and how many slots per expert to use. Total number of slots determines the amount of flops applied in the MoE layer. Ignoring the small, the routing cost. Little typo here. We need like a typo color. There we go. If the total number of slots is greater than the number of input tokens, the model will require more flops than dense transformers. More tokens will be processed. If the number of slots is lower than the original number of tokens, soft MoE will save some compute relative to dense transformers. The following experiments use a VITS backbone. MoEs have expert layers in the last 6 of 12 blocks. So what do they mean there is that you see this NX here. There's many of these blocks in an actual transformer. So a transformer is not just one of these. You have maybe 12 blocks. And here they're saying that the first 6 blocks, they're not putting soft MoEs here. They're only putting soft MoEs in the last 6 blocks. Okay. I have a limited amount of time here. There's a human child that requires my attention, but let's kind of scroll through here. Not encoder, but decoder. Yeah. Schwat. Optimal number of slots. Often unable to scale well due to a large number of experts. The model sizes range from just 38 million to 9.7 billion. Few shot evaluation. Token choice. The size is union Okay, so basically they're kind of comparing here to how expert's choice and token's choice maybe require more total parameters. There's the group size is the subset of the batch that is routed together. All tokens in a group compete to be selected by each expert. So this is the negative with previous MoE algorithms where you basically have this hard routing where tokens can only go to one expert. Thus, you end up having this inter-batch dynamics, which they don't like. But this paper, Soft MoE, does not have that because every expert sees every token, or at least has the ability to see every token. Performance and training time is a function of the number of experts. Okay, so there is some optimal number of experts here, right? Especially for token's choice and expert's choice. It does seem like as you increase the number of experts, you get a better accuracy, but at some point it goes down. So 4096 experts is worse than 512 experts. But Soft MoE does not seem to have that. It does seem like Soft MoE, you can just keep making the number of experts bigger and it just keeps working better and better. There's a little bit of a relationship here where it seems like 2048, you do get a better score than 4096, but I'd be curious what happens. I wish they would have done more experts and seen if the soft one just keeps getting better or not, or whether it also has this kind of U-shaped relationship here. And then train step time. So in the other approaches, because you're doing this routing, as you increase the number of experts, the total amount of time required increases, but the soft MoE does not have that, and it only increases a little bit based on how many experts you have. With experts and tokens choice routers, which are the shitty routers that they're comparing against, having too many experts not only hurts performance, but also significantly increases the cost. We set the number of slots per expert to 1. The next question is how many experts to use. The cost of the models are not matched. More experts will increase cost, but more experts do better. Minimum number of experts that does not lead to a strong token bottleneck in the MoE layer. Both models have the same capacity. How Soft MoE behaves when increasing the number of slots per expert. That could be kind of cool. Oh my god, these are tables though. Fuck that. Total experts, experts per layer, sparse layers. Alright, fuck that. I'm not reading that. Algorithmic Ablations, identity and uniform routing. Okay, so Soft MoE relies on learning on how to mix the tokens for each expert, right? So for each slot, there is basically a learnable set of parameters phi, which tell you the right mix of tokens or the right weighted combination, the right weights to use for a weighted combination to be fed into the expert. So the learning is not actually for each expert, the learning is for each slot, and they just happen to have one slot per expert. But that's maybe a little bit of a typo there. To understand the impact of finding useful linear combinations of input tokens, we ablate this aspect by testing several natural choices. Tokens are not mixed. First token goes to first expert and so on. Okay, so they're going to basically compare to like complete idiot routing where you're just kind of like identity routing and then uniform mixing. So are we at least better than random and average? And of course they are. It makes a ton of sense that you would be, right? If you were just identity routing, it would basically be nonsense. This isn't even identity routing. What is this? Expert choice. Total number of experts, accuracy, train time. Otherwise, the additional capacity is coming from different experts will not be used. Soft and uniform. Learn to mix tokens to create the slots, but we uniformly average over all expert outputs. This implies every input token is identically updated before the residual connections. Uniformly average. So okay, so without the final, so there's two different sets of weights here, right? There's the beginning, which is the dispatch, and then the C, which is the combination at the end. So here they're going to basically get rid of the combination set of weights, and here they're going to get rid of the dispatch set of weights. So they're kind of ablating to see which one of these actually does better. Appendix A contains further details. Okay, so this is without the D weights, and this is without the C weights. And interestingly, they're both about the same, which is kind of cool. It's interesting. It's the D and the C both seem to have an equal amount of impact. And then, of course, having both of them soft, which means that you have both the W's and you have, or that you have both the D weights and you have the C weights, that performs the best. And here they're comparing to dense. So this is if you have no soft mixture of experts. And this is fucking weird. The identity and the uniform, which is like the weird one where you're basically just routing tokens, not random. Uniform would be randomly into different experts, but for identity, you're just routing them kind of like almost rasterizing them into the different experts. That performs better than the dense. That's weird. So I'm not surprised that the purple line is the highest and that the green and the red line are kind of about the same, but I'm surprised that the orange and the yellow and the blue line here are higher than the brown line. That's fucking next level. That means that even if your routing algorithm is nonsense, your mixture of experts is actually still better than not having a mixture of experts and just using your dense vanilla vision transformer. That's some next level shit right there. Compare soft MoE with different fixed routings. Yeah, kind of crazy, right? That's kind of weird to think about. We consider the following. Actually, that's not even where I was. That's where I was. Okay. Contrastive learning experiments. We test whether the learned representations are also significantly better when used for other tasks. So learned representations, what they're basically saying is that much like they took only the vision transformer here, this is a ConvNet, but imagine this is a vision transformer and they cut off the head and then they basically trained a new head for ImageNet classification. They said, okay, well, this last layer here, which we're going to call the representation, which they learned, right? Is this learned representation better for other things, such as image language contrastive learning, right? So let's try to train CLIP, where rather than using in CLIP, they're using basically the vision transformer in CLIP, also called the image encoder. That vision transformer does not have a soft MoE. So let's see if it works better with a soft MoE. Okay, the image tower is pre-trained on image classification tasks and then frozen while training the text encoder on a dataset of image text pairs. We reuse the models in previous section, compare the performance on a number of downstream applications. For contrastive learning, we train on WebLI. Okay, so here's proprietary dataset consisting of 10 billion images and they're alt text crawled from the internet. So unfortunately for us, Google has their own image dataset that's proprietary, and that they have their own CLIP dataset. So CLIP, you need to have basically text and images. So Google has their own version of that, which is 10 billion images with alt text. Motherfuckers, just release this dataset. Like, why keep it secret? It's just so annoying to me. The image encoder is frozen. The text encoder is trained from scratch. Okay. The gaps are preserved in this setting. Soft MoE L16 outperforms VIE L16 by more than 1 to 2% and CFAR 100 zero shot. Okay, so here, this is the dense, and then now basically if you were to use CLIP but use the soft MoE, here are a couple different. So CFAR is kind of similar to MNIST or anything like that. You're basically just these little tiny data sets where you have classification, and in CFAR it's actually very tiny images. Yeah, like this is what CFAR looks like. It's like chicken, like bird, and this looks grainy. It's not grainy because of YouTube. Like CFAR is just inherently grainy. It's just very grainy, tiny images that people train on, or for these benchmarks. You can see it actually performs much better. So yeah, I mean, it does seem like we basically need to retrain CLIP but using a soft MoE vision transformer. 5. Do you get better performance by keeping dropout during inference or by getting rid of it? Does sparsity just help or something? There's no dropout here. Sparsity, just because having a routing algo that's nonsense is kind of like having a dropout in the fully connected thing. No? Is it like having dropout? Not necessarily, right? Because in dropout, you're basically getting rid of some of the activations entirely, right? So in dropout, you're saying, I'm going to come in here and I'm going to take this value here, and like rather than it being 1.05, I'm going to make it 0. So it's going to have 0 impact on the next thing. But in this sparse mixture of experts, everything is, every part of the input is being combined and then fed into every single expert. So even if there might be a situation where some of the weights are 0, and because some of the weights are 0, that token is not actually being used by the expert, but the expert, it does have there's at least a chance that every single token can go into that. I don't know if that makes sense. You're talking more about these like nonsense routings that they have here, where they were saying identity routing. It doesn't sound like any of the tokens are dropped out, so I don't know. It seems like all of the tokens are going to every single expert. Hopefully that answered your question. I don't know if that answered your question. I'm sorry, Luke. Right. Okay. I don't think you trust me. You're like, this guy doesn't know what the fuck he's talking about. Performance of models trained with increasing experts. One slot token per expert with a matched training duration. Total number of steps is computed to match the total training time. Dashed line corresponds to a dense. So obviously a dense VIT, there's no notion of experts, so it's going to have the same level of performance no matter how many experts there are, because that's not even applicable. So that's kind of why it's a straight line. So this is just the performance of a dense model. And then you have soft MoE versus expert's choice. And here the group size, I think, is they're referring to how many other images in the batch can influence the selection of the tokens. So obviously soft MoE beats it, dominates it. Still possible that some tokens contribute a little to all slots if their logits are much lower than those of other tokens. While there is no dropping, yeah, so maybe this question right here is exactly what you're talking about, Luke, where it's like there's no dropping, but if some of the tokens are basically, if some of the weights are basically 0, then some of those tokens are basically not going to contribute at all, and they might as well effectively be ignored. Some tokens contribute to slots in a disproportionate manner. Shows the distribution of cost tokens for the total weight each token provided. This is computed over a batch with 256 images, 196 tokens. Heavy tail of tokens that provides stronger total contribution. Figure 9. Okay, so the per token sum of the dispatch weights. Dispatch weights are the weights that basically determine the weighted sum of the stuff as it comes in to the experts. So it's the red, it's this stuff here. This is the dispatch weights. Where is it? This paper is so long. These are the dispatch weights right here, 0.9, 0.4. So what they're kind of asking is like, what is the distribution of these dispatch weights? Is it the case that that there's basically 1 or 2 dominant things here, such as the 0.3, 0.4, and then everything else is just numbers very, very close to 0? Or is it the case that you kind of have a lot of contribution, every single token contributes a little bit? Like, is it just a handful of tokens contributing pretty much everything, or is it all tokens contributing a little bit? So Around 2 to 5% of the tokens provide a summed weight above 2. Also between 15 to 20 contribute up to 0.25. The last layer is slightly different, where each contribution is softer tailed. Okay. Expert contributions. We would like to understand how much different slots end up contributing to the different output tokens. Okay, so they're kind of like this here, token contribution, expert contribution, number of input tokens. They're kind of trying to see like what is the actual signal coming through this soft MoE? Like, what does it actually look like? Approximate the total contribution of each expert. How much is each expert contributing? How much is each weight? How is the dispatch weight also distributed? How is the output combination weight, or whatever it's called, distributed? Some experts can input output tokens between 3x and 14x more than others. So you do have some dominant experts. How many input tokens are required to achieve certain cumulative weights? Distribution varies significantly. Only a few slots. For a few slots, the top 20 to 25 tokens account for 90% of the slot weight, while for other slots, the distribution is more uniform and many tokens contribute to fill the slots. That's kind of interesting. We see that slots tend to mix a large number of tokens, unlike in standard sparse MoEs. So you are kind of getting interesting, complicated behaviors where slots are either kind of like really only paying attention to a few things, or they're paying attention to kind of a lot of things. In order to provide some intuition, Figure 10 graphically shows the linear combination for 8 different slots shown in Figure 1. Linear combination for 8 slots, and because they have 1 slot per expert, it might as well just be a linear combination for 8 different experts. 1 slot per expert. And you can see how there's one expert that's definitely paying attention to the bill of the duck. You have one expert that's definitely paying attention to the head. You have another one that's definitely paying attention to the eye, maybe one that pays attention to the whole thing. So there's definitely like some semantic meaning to the slots here, is what I'm seeing. And if you look, this one here is definitely the background. So you see how it kind of seems to be paying attention to all the different tokens. The selected slots are cherry-picked to highlight the differences among slots. Okay. Yeah, exactly, right? Even me, like, I'm even using the word paying attention to, right? So like that phrase, pays attention to, is basically comes from like the way that attention maps work, right? So that's I'm using terminology from attention mechanisms to describe the routing in this mixture of experts, soft mixture of experts. So it is very much basically attention. It's just like it is like an attention mechanism, which is just kind of cool to think about how we kind of came to attention mechanisms through a mixture of experts. Like there's this whole idea of like, hey, how do we route these experts and blah, blah, blah. And like what they ended up on is an algorithm that looks a lot like attention. So it's almost like everything just converges towards an attention mechanism. Yeah. It's kind of cool. It's like, all right, so here you have the different dispatch weights, and these are so they only have the mixture of experts for the last 12 layers, or the last 6 layers, and obviously I think this is 0 indexing, so that's why it only goes up to 11. But you can see the combined weight across, average combined weight across tokens, so you can see how the experts, different experts, so maybe the one that's down here, right, has a small weight across a lot of tokens, and then the one that's up here has a very high weight across a smaller number of tokens. And there's definitely some kind of dependence depending on how deep you are in the neural net, or in this transformer, vision transformer, to the relationship between how much are you focusing or paying attention to a small number of tokens. The dispatch weights for 99.5% are summed over all the slots of 1. Only a tiny fraction of tokens contribute to slots by summing more than 3. Distribution of combined weights per slot summed over all input tokens. Dispatch weights from all tokens assets add to 1. Okay, so I mean, this is basically just... I feel like this plot is not as good as this. Like, I like this so much better. Right, just showing me exactly what individual slots care. Like, this slot here has some specific set of weights, and those weights, or that slot there has a specific set of learnable parameters. Those learnable parameters are used to determine the weights, and those weights are basically corresponding to a specific semantic subset of the total tokens. Pretty badass. Okay. Sparse models can face infrastructure challenges, which may have slowed down their broad adoption. Since these models were originally conceived to unlock massive model sizes, they tend to be distributed, and most routing algorithms require additional communication costs. Additional activations, gradient, expert parameters are sent across devices. This is also true for soft MoE, where experts may be distributed. However, modern dense models are now sufficiently large that they are also distributed. Yeah, so you're already doing this anyways. So closing the gap in this axis. The benefits of sparsity shine at small model scales, both in prior work and with soft MoE, fitting with the current needs of the industry for faster inference. Yeah, especially we've talked about, or we've been looking at some robotics papers where basically we're realizing as a community that like all these different pieces in robotics can just be replaced with a language model. But now we kind of are in the hard part where, okay, well, if we want to replace everything with a language model, how the fuck are we going to replace a robot control algorithm with a language model when the language model inference is like 100 times slower than it needs to be, right? These robots need to run control loops that are hundreds of hertz per second, and we certainly don't have inference at 100 hertz per second. So maybe sparsity and this type of stuff with the soft MoE is a way to get much faster inference, and eventually this is kind of the path that we end up taking for using LLMs for these fast control loops. But I don't know, that's just kind of the first thing that I thought of there. Presented soft MoE, a new sparse transformer architecture that avoids the discrete token expert assignment problem that is common in sparse mixture of expert models. This discrete assignment problem, and because it's discrete, it's not differentiable, right? And that's a big problem. By merging input tokens into linear combinations before dispatching them, right? This is the weighing. We're able to train a fast and fully differentiable model so you can learn it. We perform extensive image classification, image language contrastive learning experiments comparing the performance, and the performance is fucking amazing. Soft MoE is surprisingly effective and strongly outperforms, one could even say dominates, the other approaches while being computationally cheaper. How to deal with causal masking for language decoders is an exciting and impactful research direction for future work, and something tells me that OpenAI kind of already has their own way of doing that, and they just are keeping it secret. Cool, so that is the paper. There's a bunch of appendices here, but I do have to go, so I'm just going to take a sip here and give a little summary, and then we'll go from there. Attention does matter. It's not all about size. This is funny. It's like the opposite of those MLP mixer type papers that came out where they tried to get rid of attention and only have MLPs. It turns out if you try to make the best possible MLP, you end up on a mixture of expert MLPs, and then the mixture of expert MLPs, the best way to route into that mixture of experts is effectively an attention mechanism. So no matter what, you just end up on this attention mechanism. Can you go through all the steps again briefly when you summarize the paper? I don't know exactly what you mean, Chris, but I'm going to try to summarize it as best I can. So here, today we read a paper called From Sparse to Soft Mixture of Experts out of Google DeepMind, released on the 2nd of August 2023. This is a paper that kind of builds on previous work by Google. For example, Sparse Mixture of Experts, and even before then there was a Pathways, which is kind of another paper in the same vein. So what this paper is largely trying to do is it's trying to replace the feed-forward block here, this fully connected little neural net here, in a vision transformer, although you could effectively do the same thing in a language or text-based transformer as well, and is trying to replace this dense little feed-forward block with a mixture of expert feed-forward blocks. So here you have an expert's, kind of sounds fancy, but basically you just think of it like it's another version of that little multi-layer perceptron, right? Little MLP layer. But once you do that and you say, okay, well, rather than using one dense one, let's use a couple different sparse ones. Now you run into the problem of, okay, well, how are we going to route specific tokens that are coming out of this attention map mechanism here and are being normalized? How are we going to route them in there? And so one way that they kind of naively try to do that is here, okay, you just route naively into each expert. And then this previous work here, which they call sparse mixture of experts, creates this kind of score function here, and then that score function is used to sort into specific experts. And that's what they're comparing to here with this sparse MoE, where specific experts, specific little layers, or specific ones of these experts here only receive a subset of all tokens in the image, right, where each token is just a patch. What they do in this paper, which they call Soft MoE, is that every expert receives effectively every token. And the way that they receive every token is that they're not receiving actual tokens that exist in the image. What they're receiving is a weighted combination of tokens that exist in every image. So it's literally just like 0.3 times this token plus 0.4 times this token plus 0.001 times this token, and so on. And the reason that is such a kind of a big unlock is because this is fully differentiable, right? If you have a gradient that's coming in here and it's coming in through this expert, you can take that gradient and then go to every single token here, right? Because this token here is a weighted combination of every input token, which means that if you're doing a back propagation, you can back propagate into every single token. Versus here, you can't do that because here you have a hard, discrete assignment that's happening, right? So you're not going to be able to back propagate through that hard, discrete assignment. Okay, so what else? Every expert, there's a slot which corresponds to one per expert. Here it sounds like there's multiple slots per expert, but then once we read the whole paper, we figured out that they basically narrow on there being one slot per expert, and each slot has a per slot set of learnable parameters phi, and these learnable parameters phi basically determine what the weights are going to be, such that you combine all the input tokens into one kind of combined token, and that goes into that slot, and then what comes out, you have these combined weights, which then combine what comes out, such that you can get basically the same amount of tokens in as out. And those slots, each slot behaves slightly differently, and each slot is learned over the course of training. And much like the heads in a attention mechanism, the slots kind of learn specific semantic concepts, which they show in this picture here, which I think kind of like is the best picture. Can I find this? Right here. So you can see how each slot, and because there's one expert per slot, it's basically each expert is picking up on different concepts, semantic concepts, such as the head of the bird, the bill of the bird, and so on. Okay. So that's, I guess, what Soft MoE is. And what else does this paper go into? This paper is actually pretty good. It goes through it like there's a lot of different sections here. They talk about comparisons to other approaches. They also spend a lot of time thinking about what this means. I think one of the more interesting things that they talk about is that this is effectively an attention mechanism, right? They're realizing that this is very similar to an attention mechanism. Similarities with Soft MoE, which actually we came to the same conclusion. Some of our... What else? merge, mixer, fuse, some limitations. So they haven't figured out how to do this for the decoder part of the attention, or the decoder part of a transformer that you would use in a language model, because the decoder part of a transformer that you would use in a language model requires this masking, and that masking means that you couldn't actually do a weighted combination of all the tokens. You'd have to figure out how to mask that. So they leave that for future work, but we suspect that I have to feed this baby. Okay, but we suspect that OpenAI might have already figured out some way to do sparse MoE and masking in a language transformer decoder, so there might already be a way to do that. And, okay, that's that. There are some hyperparameters for this. You have to pick the number of slots, and you also have to pick the number of slots per expert, and you also have to pick the number of experts. So there's a bunch of different hyperparameters for Soft MoE, and those hyperparameters are going to depend on the hardware, so that's a whole other series of problems of how to pick the right values for those, depending on your hardware. And then this paper just has a bunch of experiments where they train a bunch of different vision transformer models, a bunch of different sizes of vision transformer models. They train them on a task. They train it on a kind of a fine-tuning, two different types of fine-tuning. One type of fine-tuning where they basically cut off the head and then train for an extra kind of on a small data set, and then fine-tuning, full fine-tuning. And kind of to cut to the chase, it turns out that no matter what benchmark and what weird task they can come up with, the Soft MoE pretty much performs better in every single way. The small, whether it's a small model or a big model, whether you're doing transfer learning, whether you're doing fine-tuning versus this 10-shot cut off the head type of fine-tuning, it pretty much works better in every single way. And if you compare it to other types of MoE, so there's other variants of MoE that people have done before. I think they introduce expert choice and what they call token choice, and it pretty much beats those out of the water as well. So it seems like this model is basically the best ever. Or this technique, this sparse MoE technique is going to dominate. That's all I got to say about that. I'm kind of distracted, so sorry about that, but I'm always coming into the stream late. Sorry about that, Creative Builds. Soft MoE. Yeah, I might have said the wrong thing 10 times there, so apologies. What if you get rid of the prefix attention block and only use MoE? I don't know. That's a whole other area of research. Is like, what if you get rid of this multi-head attention? You just have like 500 of these soft MoE blocks just right on top of each other. Does it work? It might be the case that it still works. And not only does it still work, but it works even better. So maybe soft MoE is all you need, which I think someone said on this stream as well. What is your starting stream time? I start at 8 a.m. Central Time because I'm in Austin, Texas, but I don't know. I could stream at different times depending on what you guys want. I don't know if you guys want earlier streaming, later streaming, but I don't know. Right now I'm just kind of streaming on in the morning because that's just when I have time. But later, okay, I can do later. So anyways, that's sparse to soft mixture of experts. Pretty cool paper. I like it. Thanks everybody for commenting. Thank you Christopher, Luke, JM, Joseph, Ed, Mabongeni, Abhishek, Darshan, Kalina, Joseph, John, Ed, everybody. If I missed your name, I'm sorry. Joao, thanks for listening. Thanks for watching. Hope this was interesting. Hope this was inspiring. Go out there and do something cool today. And see you guys later.